Alrighty. So we're just starting out with a basic example here. So remember again, we use capital letters when we are talking about the angles, and we are using smaller case letters when we are talking about the sides. And of course, we always keep C for the hypotenuse sides, which means C, capital letter, would become the 90-degree angle then. So here you can see we have our 90-degree angle, and they are giving us one angle measurement, and they are giving us one side, right? But we know since this is a right triangle, we actually have two angles given to us. We have that 90-degree angle, and then angle A is given to us as 34.2. So what they're asking you here basically is to find all the missing angles and sides. So as you can see, to start out by finding the missing angle, which would only be angle B, you can technically use the idea of if 90 degree is that angle C, the other two angles also have to add up to 90 degrees, right? Because what's the total of the three angles in the triangle?
180.
180, right. So if your corner angle here is 90, then the remaining two are also 90. So you're literally just taking 90 minus the given angle A to come up with angle B, which in this case comes out to be 55.8. Now, as far as finding the sides A and C, they're giving us side B as 19.4 units. So you can actually use, again, your trig functions to find those missing sides. So you can see for finding side A, we're actually using the tangent function opposite over adjacent. Since we already have the adjacent side, you can use the angle measurement and 19.4 to calculate your side A. So that means tangent of 34.2 would be missing number x over adjacent side of 19.4. And you can see we end up multiplying 19.4 with tangent of 34.2 degrees to get your 13.2. And we're actually using that same idea to find the hypotenuse. And this time we're using the cosine of A function adjacent over hypotenuse to find the missing side of the hypotenuse. Now, one thing I will tell you guys when you're working through these, always try to go with the given values. So since they gave us the 34.2 angle and they gave us the 19.4 as the side, you probably want to do calculations involving those numbers, because usually what happens is when the missing sides you are finding will be rounded answers when you're doing these calculations. So try to avoid as many rounded answers in your calculations as you can. So stick with the original values that were given to you. So that's pretty much the same thing we are doing here in problem number 1. They're giving us our triangle. We have one given angle and one given side, but again, we know this guy is a 90-degree triangle. So let me do a quick sketch. Oh, come on. Okay, so we know this is a 90-degree angle. Your side B, your side A. Angle A is given to us as 20 degrees. Side B is given to us as 15 units. And you're trying to find side A, side C, and angle B. So again, I'd probably start by finding angle B first, which would be 90 degrees minus 20 degrees, right? So he comes out to be 70 degrees. Okay, then let's get into sides A and C. So which one do we want to find first, side A or side C? You want to find side A? Alrighty. So if you're using 20 degrees as our anchor angle, what function can I use to find side A? You can go back to the tangent function, which would be tangent on which angle? B?
A, sorry, A.
Actually, it wouldn't matter because they're both going to be using the same opposite and adjacent sides, right? So actually you can try it. Let's try it with B. And the reason we can use B is because B was not a rounded answer, right? If B was a rounded answer, then I'd probably fall back to A. All right, so angle B, what would be your opposite side now? 15. And then, of course, adjacent would become the side A itself. So angle B is now 70 degrees. So you have tangent of 70 degrees equals 15 over a. So the idea is to get a by itself and move everything else to the other side. So you're basically solving an equation at this point. Start by multiplying both sides by a. And then, of course, we would need to divide both sides by tangent of 70 degrees. Again, please make sure your calculator is in the right mode. So that will be 15 divided by tangent of 70 degrees.
We need to be in degrees, right?
Degrees, yes. Very good. And what are you seeing as your answer? And let's do 2 decimal places for our rounding.
5.46.
Very nice. So your wrong answer is 5.459. So in 2 decimal places, that will become 5.46. And they didn't really give us measurement on the sides. So we don't know if they're inches, feet, centimeters. So we'll just leave it. No units today, which is weird, but applications, they'll definitely give you units, okay? All right, so we found side A. We found angle B. So the last part is finding side C. Now, how can you find side C?
By using cosine.
Yeah, so you can fall back to, again, using sine or cosine function, right? Because both of them use hypotenuse in it. Technically, you can also use Pythagorean theorem because you have 2 sides. But with Pythagorean theorem, what's going to happen is you've already rounded 5.46, which means that answer is going to be even rounded further. So be careful. If they were originally giving you the 2 sides, then you would be okay. So in this case, go with sine or cosine function. So we are finding side C. So what are you guys thinking about, sine or cosine? Cosine? And on what angle? Cosine of A?
Yeah.
Alrighty, so that would be adjacent over hypotenuse, and that was a good choice because then we're avoiding using that 5.46 calculation in there. So that's going to be cosine of 20 degrees equals 15 over C. Pretty much the same kind of calculation like we did with our tangent function. Multiply both sides by C, and then you would divide both sides by cosine of 20 degrees. Okay, and what are we getting for this guy?
15.9626.
Alrighty. And then keep it at 2 decimal places, so 15.96, right? Anybody have questions on this? Okay, so 15.96. And you should have all your 3 angles and all the 3 sides, right? Okay. So now we're, of course, going to try and apply all of these techniques into applications, which is what your example 2 is starting out with. So this one is saying you have a mountain that is 5,000 feet height, and you can kind of see that image to guide you along. The distance between the peak of that mountain and an adjacent mountain is 25,000 feet. The angle of elevation between the 2 peaks is 27 degrees. So they want to know what would be the height of the adjacent mountain. Okay, so this little guy here is 5,000 feet tall, right? They're saying from the peak of the first mountain to the second mountain, that's a distance of 25,000 feet. We know the angle of elevation, I guess, if you're standing at the summit of that smaller mountain looking up, is 27 degrees. So they want to know what is going to be the height of this taller mountain. So as you can see here, we're starting out with the sine function because sine would be opposite over hypotenuse, right? And those are the numbers we know. We know angle 27. So using the sine function, they actually come up with what this distance here is going to be, which is going to be horizontal, right, to this peak of the smaller mountain. And that distance actually comes out to be 11,350. But as you can see, that's only this part of the mountain, which means we still have to consider this height of 5,000 coming from here. So that's why they're actually adding 5,000 to it to give you the complete height of that taller mountain. Does that make sense? Okay, very good. So let's look at what our example here is talking about. So they're telling us we have a ladder that is 16 feet long and it leans against the side of a house. The angle of elevation for the ladder is 80 degrees, and they want to know from the height, no, sorry, find the height from the top of the ladder to the ground. So it may not be a bad idea to try and come up with an image for this guy. Okay. So we're talking about the side of the house, and we have a ladder that's leaning against it. I probably made it leaning too far out, but we'll still get the idea, right? So they're telling us the length of the ladder is 16 feet, right? Okay. And they're also telling us it is making an angle of elevation, which is 80 degrees. Now, where would you place that angle? On the ground or where it's meeting the side of the house?
Is it the side that is meeting the house?
Is it the side that's meeting the side of the house? No? So which one is it then? Yeah, because angle of elevation, remember if it's in your line of sight, you always have to look up for angle of elevation. So it's actually this guy right here, which is the 80-degree angle, okay? And that's actually going to be the crucial part is, kind of coming up with that image and trying to figure out where these measurements need to be placed when you're doing these calculations already. Okay, what else did they tell us? Is that it? That's it. And they want to know the height from the top of the ladder to the ground, which means if this is the top of the ladder, they're asking you to find this distance, right? All right, so looking at the right triangle, of course, this is where your 90-degree angle is going to be with the house and the ground. What function would help us come up with that h value?
Would it be sine?
Yeah, because that's the opposite side. The length of the ladder is making the hypotenuse. So that's going to be the 16 feet. So opposite over hypotenuse is going to be the sine function. So that's going to be sine on the 80-degree angle, opposite over hypotenuse, which will be h for 16, right? So what does that height come out to be? Alrighty, multiply both sides by 16. Okay, 15 point.
756.
So it's 2 decimal places, yeah. Alrighty, so that's 15 point, whoa, 756. And what's our unit of measurement here? Very nice, thank you. Feet. Please make sure for applications you are including units of measurement. Did anybody have a question on this example or how we came up with that? So basically get your image and then look at where your given information is placed, and then based on that you would have to decide sine, cosine, tangent, or even sometimes does it make sense to bring one of those inverse or reciprocal functions in. But if you can do those, you can probably use the original 3 functions, right? Alrighty, let's go on to our next example here. So this guy here is talking about at a point from the base of the building, so this is our building right here. So 200 feet away from the building, your angle of elevation to the bottom of the smokestack is going to be 35 degrees. So that's that smaller angle there. Whereas the angle of elevation to the top of the smokestack would of course be 53 degrees. They want to know what's the height of the smokestack, right? So two different angle of elevations, but they are still looking at it from the same distance of 200 feet away from the building, right? So if you look through the calculation, they're going to be doing this basically by using two different right triangles. So you've got a 35-degree angle with the opposite side, which is side A, and the adjacent side of 200, right? Tangent function. So they're basically trying to calculate the height of the building, and that's going to come out to be approximately, well, I guess they didn't really calculate the numbers. They just did 200 times tangent of 35 degrees. And then for the next one, what do you think they're doing there? The A plus S, what is that? Yeah, so that's the height, that is the building and the smokestack together, right? Because at 53-degree angle of elevation, you are now looking at the entire length of that building with the smokestack. So that's the value that actually comes out to be 200 feet again from the building at an angle of 53 degrees, so tangent of 53 degrees. And then you're going to have to subtract the two values, which is what will come out to be 125.4. And you know, the main reason they didn't evaluate what A is separately or what S is separately is again to avoid rounding error. So that's why they left it at 200 times tangent of 35 degrees and then 200 times tangent of 53 degrees. And then they're letting the final calculation happen when you're trying to find the height of the smokestack, which is S. So let's see what we've got here for our example. At a point 65 feet from the base of a church, the angle of elevation to the bottom of the steeple and top of the steeple are 35 and 43 degrees respectively. So find the height of the steeple. So about the same thing as our smokestack example. Okay, so again, we've got our church. 65 feet away from the church, we are looking at angle of elevation to the bottom of the steeple, which is at 35 degrees, and then to the top of the steeple, that angle is 43. So the bigger angle is 43, the smaller angle is 35. And these variables, again, it's up to you, but you can use C for the height of the church building, and then you can use S for the height of the steeple if you like. So again, what function would we use here to even start out with? Let's say we're doing the 35-degree angle first.
Opposite, or we can use tangent or opposite over hypotenuse.
Opposite over hypotenuse, but then that means we need to calculate the hypotenuse, right? So we don't know what the hypotenuse is, so yeah, you're gonna have to go with the opposite and the adjacent sides. So just like your example 3, start out by taking 35 degree angle with the tangent function, which would be opposite over adjacent, and your opposite side would be side C. Adjacent side is the 65 feet. So again, your value of C would come out to be 65 multiplied with tangent of 35 degrees, right? And leave it there because again, we don't know if we're going to be getting decimal answers or nice, clean, exact answers. So let C stay as it is for now. Okay, now we want to know what's the total height of the building with the steeple. Bless you. So that's going to be on the bigger angle. So that would be tangent of 43 degrees which would be the opposite side, but for 43 degrees, your opposite side is going to be both the length of C and S added together, divided by the adjacent side, which is 65. So if it kind of helps, let me see if I can do this in color. So let's say our smaller triangle, which we did first, was this guy here in green. And then the bigger triangle is where we're taking the entire length in red. Okay, so again, multiply both sides by 65. So that's going to be C plus S equals 65 times tangent of 43. Now, you know, at this point, you are basic equation solving again. So if you are given 65 times tangent of 43 degrees, we know side C, we can write it as 65 times tangent of 35 degrees plus S. And this is why you end up subtracting when you're trying to get S by itself. So anybody have the answer for S? Oh, okay. Okay, so you're doing 65 tangent of 43 minus 65 tangent of 35. Oh, missed a number in there. There we go. Alrighty, so 15.0999. Okay, and this is the height of the steeple. And what's our unit of measurement again? Feet. Anybody have question on this one? No? Alrighty, let's see what this guy is doing here. Okay, now remember, angle of elevation is if you're from your line of sight looking up, angle of depression would be looking down, right? So here they're talking about a swimming pool is 20 meters long and 12 meters wide. Okay, the bottom of the pool is slanted so that the water depth is 1.3 meters at the shallow end and goes down to 4 meters at the deep end. They want to know what is the angle of depression to the bottom of the pool. So they're telling us the pool is 20 meters long, 12 meters wide, right? Which in this case, I'm not sure that 12 meters is going to make a difference in our calculation. At the shallow end, you're at 1.3 meters. At the deep end, you fall down to 4 meters, right? So you can actually see they took that shallow end 1.3 and subtracted it from 4 meters to give us this 2.7 meters here, right? Everybody understand that? Okay, so angle of depression is actually going to be right here from this horizontal level, that little red line that they have. So this angle of depression from the horizontal going down to the bottom of the pool. So I have, if you look at this little triangle here, I have my adjacent side and I have my opposite side, right? So since we know the adjacent and opposite, that's why they're using the tangent function. But this time you're actually calculating A, the angle. So opposite over adjacent would be 2.7 over 20. As a decimal, you get 0.135. But since tangent of A equals 0.135, to get A by itself, you actually have to get rid of the tangent function, and we do that is what undoes tangent is arc tangent or tangent inverse, right? So that's why they're using arc tangent on 1.35 to give us the angle A, which by default, remember you always get radian answers. So you're getting in radian 0.13419 and then convert it to a degree to get 7.69. So basically what's happening right here, where you have your tangent of A equals 0.135, they're taking tangent inverse on both sides, so that your tangent and tangent inverse cancel out, and you're doing tangent inverse on 0.135. So that's how they actually came up with this statement here. Okay, let me check. So you are doing arc tangent. So by default, this actually gives you your answer in radians, but I think it will really depend on what mode your calculator is in. Because when I have my calculator in radian mode, I'm getting 1.34188. Yeah, so I'm getting that answer. And then let's change it to degree. And I'm getting 7.688. So that's rounding up to 7.69. And you said you didn't get that? You were in radians? Okay. So it looks like as long as you have your calculator in the right mode, you actually wouldn't have to worry about converting it using that pi over 180 or 180 over pi. So I would say look at the instructions in what mode they want you to give the final answer. All right, so what are you guys going to do for example 4 then? From a time a small airplane is 100 feet high and 1,600 ground feet from its landing runway, the plane descends in a straight line to the runway. Again, they want to know what the angle of descent, and again in degrees, of the plane is going to be. So let's see if we can come up with a nice little triangle here to help us out. Okay, so from the time a small airplane is 100 feet high, so that's going to be 100 feet high from the ground, right? They're telling us you are 1,600 ground feet from its landing runway. So the moment it hits the runway, right? Your ground distance is 1,600 feet, okay? They're asking us to find the angle of descent. So again, the question is, which is the angle of descent? Up at the top. Very good. This is the angle you're going to be finding. Very good. It's going to be tangent because you're still doing opposite.
Because you're drawing like that.
Yeah, you can do it. Because that's your ground distance. This is your. So where's your plane at? Is the plane supposed to be here?
It would be here.
Or you're going that way?
See.
Trying to think, will that work? Because if that's your angle, your opposite side is going to be 100, and the adjacent side would be 1,600. I am not sure, Jose. I'm going to have to see what that calculation looks like. Because you would be doing opposite over adjacent. And then you would be doing tangent inverse on that value. Yeah, looks like it actually does work. So this is what Jose has on his paper. So you are at a height of 100 feet, 1,600 feet from the ground, and this is the angle you are using, right? Okay. So it actually looks like that would work also. That's what you guys did also?
Well, that's what I did.
That's what you did? Okay. So that would be tangent, I guess we'll call it theta, opposite over adjacent. So with this guy, opposite would be 1600. But then I think I'm going the other way. Okay, let me show you with what I had first, and then I'll come back and show you what Jose had and the rest of you had, I guess. All right, so 1600 over 100, which would of course come out to be 16, and then you would do theta equals tangent inverse of 16. So this guy will actually give you, oh, where are you? Tangent inverse of 16, and we want this in degrees. Yeah. This guy will actually end up giving you 86.42, I guess. But what you are actually going to have to do is subtract that from 90 degrees to get, oh, what are you? 3 point something. So that's going to be your angle. So actually, it might be better to do it the other way, because then you would have to do the subtraction. You're starting out directly with 1 over 16. Theta would be tangent inverse, which should give us directly the answer we want. Did you get that?
Yeah.
All right, awesome. Yeah, so the raw answer is 3.576. So 3.58, and remember this guy will be in degrees. Yeah, so I think I actually like this way better than, because then you're not having to worry about messing with your angles, because yeah, it will come out to be slightly different. So let's go with this way. Did anyone have questions on that one? Are we all okay? Okay. Now, this part here, we are getting into bearings, which is of course, when we talk about directions for surveying and navigation. So they're basically saying a bearing measures the acute angle that a path or line of sight makes with a fixed north-south line. So your bearing again is going to be acute angle. Remember, acute again means less than 90 degrees, right? That's going to make that the path or line of sight will make with your north or south line, okay? So in this case, we are talking about this guy right here, the south 35 degrees east, which of course you're talking about, going 35 degrees east of south. Your north 80 degrees west, which is this middle diagram here, is of course your 80 degrees west of north, and northeast 45 degrees would of course means 45 degrees east of north. So your bearings will give you both your, I kind of think of it as horizontal and vertical directions, right? North and south would be going vertically, east and west would be going horizontally. And we're actually going to be looking at how this plays into our angle calculations when we are doing our little trig functions here. So they're talking about in air navigation, bearings are measured in degrees clockwise from north. So if you're talking about starting at north as being your 0 degrees, you can kind of see how that whole value changes, right? So kind of a little bit different from what we were doing in unit circle. At north, we're starting at 0 degrees, and then you're actually going clockwise. So every angle has now actually changed places, basically. So 0 at north, that means east would be 90 degrees, south at 180, west at 270, and of course, if you go back up, you're at 360. So you can kind of see how those angles are now measured. So this might be something that, we're going to have to kind of remember when we are working through examples and on exams. because now your directions are not as we normally do with unit circles. Okay, so let's look at this example here. Finding directions in terms of bearings. So they're telling us a ship leaves port at noon and heads due west at 20 knots or 20 nautical miles per hour. At 2 p.m., they're telling us that the ship changes course to north 54 degrees west. So again, basically, remember you're going west of, or you're going north of west, as shown in the figure below. Okay, so they are basically asking us to find the ship's bearing and distance from port at 3 p.m. So in this image, first of all, where's your port at? Sorry?
I see.
I thought you said something.
It's
It's E. It's E.
It's B?
They go at 20 now for a while.
They start at point A actually. So they started at point A, but remember they were going due west, right? So, sorry, they were going due west, which means they were going just out west. They hadn't kind of taken that northwest route yet. So they just started out going west. And then once they reached 2 p.m., I guess, the ship changed its course and started going 54 degrees northwest, basically. And then at 3 p.m., I guess they have traveled, what are they doing? 20 nautical miles per hour. So that's an hour later. So they are 20 nautical miles after that. So you've actually got a little calculation here. So for 2 hours, they traveled because they left at noon. We're talking about at 2 p.m. they changed direction. So that's 2 times 20 nautical miles. So that's where they get that distance of 40 nautical miles. We know if this is our north and south line, then this is going to be our angle here, which is at 54 degrees northwest. And then they traveled another hour and they are at another distance of 20 nautical miles. So now they want to know basically the ship's bearing and the distance from port. Alrighty. So the first thing, of course, we are coming up with is what is this angle right here. Okay, so that's going to be your 36 degrees because we know if this side here is 90 degrees, then this side should also be 90 degrees. So that's 54 minus 90, which gives you this little angle here. I'm not sure quite what to call it. They seem to be calling it angle B, 36 degrees. Then they're getting into the side B. And, okay, side B is this measurement right here. They're using the sine function on 36 degrees times 20 to get the side B. And then, of course, we need to calculate side D. So now they're using the cosine function, 20 times cosine of 36 degrees to get your side D. But we are interested in the total distance from the port and the bearing itself. Okay, I see that. Okay, so now they're actually using the bigger triangle ACD. And instead of going back and forth, if you guys can see on your paper, the bigger triangle ACD, they're actually trying to figure out what that original angle A is, right? Because that will give you the angle from the port, how far away they are from the port itself. And then B plus the 40 nautical miles that they traveled going west will give you the adjacent side. And side B would be your opposite side. So you can kind of see how they did that little calculation there and came up with tangent of A was 0.209. And then same thing, you're using the arc tangent function to figure out what that angle A is. So basically, the initial thing that we did was we figured out what this little tiny angle is here, which is kind of forming in that little, I guess, BCD triangle, right? So find that, then they figured out what would be the measurements for side B and side D. Now, once you know side B and side D, then we are falling back on this bigger triangle now, because we actually are interested in knowing what this angle is, because that's the angle from the port to the ship, which would be your bearing. And then the distance, the distance would be, of course, this side C that we're trying to find. So they're using the tangent function to come up with this value, d over d, and for d, we would need to add this side plus that 40 nautical miles. So that's actually what they've got right down here. This here is your side B, which is the opposite side to angle A, and then side B plus the 40 nautical miles gives you the adjacent side. And then you can actually calculate your angle A, but that also means after you calculate your angle A, you need to come back and find that distance of your ship from the port, which is now side C, or basically this longer side right here. And again, they're falling back on the sine function to help us out with that. So B over C calculation. So it's a little kind of interesting on how you have to break apart your triangle into two smaller triangles and then use that to come up with a big triangle. And we're actually going to be doing something similar here with example 5. Okay, so we'll pick that up next time. All right, so you guys are coming prepared to take a quiz on 1.7. We'll do 3 questions, no graphing, and no calculator approximations, because that's literally just typing numbers in a calculator and coming up with an answer. So we won't do that. I know, sorry. And no graphing. So look at the other types of examples in that handout. Look through your homework, and we'll do that on Thursday. Okay? All right, guys, have a wonderful day.